In the third part of this video lecture, we are going to state and prove the dominated convergence theorem. At this part, we're discussing the meaning and interpretation of these theorems. Their examples and applications and corollaries of these theorems will remain be left for the next video lecture. For now, let's recap what we said so far. We are analyzing what can happen to the integral or even the expectation of random variables, which is a particular case of integral, when we have a function that has a parameter n, and that parameter is varying, what can happen to the integral of those functions. And we see here this green area, it has area 1, but we cannot really see it has area 1 because it's far and it's going to infinity, it's disappearing. And here we can also have this red region here also has area 1, but we cannot really see that it has area 1 because it disappears to infinity. And to make that precise, we consider what is the function that we get when we let n tend to infinity, and that function will not, the integral of that function will not be 1. This is what we mean by losing mass. We saw the monotone convergence theorem saying that we neither lose nor gain mass in the limit if the functions are non-negative and non-decreasing. Then we saw a very general result, very general property of convergence of functions, which is, well, forget the lim-inf here. Just if this was a limit, if these functions have a limit, and the integral of those functions also have a limit, and these are non-negative extended Borel functions, then what this says is the integral of the limiting function can be at most equal to the limit of the integrals of those functions. And this is consistent both with the monotone convergence theorem, which says this will be equal under certain conditions, and the examples we showed before, where this was smaller. And now we are ready to state the main theorem of this section, which is one of the main theorems of probability theory and measure theory. It says, if a sequence of functions is bounded by another function which is integrable, okay, so if the sequence of functions, in absolute value, they stay between plus g and minus g, where g is an integrable function, so g has to be non-negative because it's bounded from below by the absolute value of something, and assuming g is integrable, so its integral is not plus infinity, then these functions fn, they can do whatever they want. If they have a limit, then the limit will be respected by the integral, which means the problems we saw before here with these losing mass cannot happen. What can happen is just that the limit of the integrals will be equal to the integral of the limit, which is very useful, as we'll see in the upcoming video lectures. Well, how can we prove that? Well, first, let's replace almost every omega by every omega. That will be convenient. And then just notice the following. We want to use the previous result. We want to use the previous property, which is a Fatus Lemma. Fatus Lemma is very general, and it only requires that functions be non-negative. How can we get a non-negative function here that will be useful? Well, from this, if we want to get a non-negative function, one way is just get the fn and add g to it. When we add g to it, then this becomes a non-negative function. And moreover, well, since we are assuming fn converges to f, then we have fn plus g converges to f plus g. And now we can use Fatus Lemma. So this is the proof already, assuming convergence holds everywhere. We can use Fatus Lemma to say that, well, in this case, the integral of f plus g will be bounded from above by this limit, or lim-inf, of the integral of fn plus g. But now we notice the following. G is integrable. Its integral is finite, which means we can take it out here. No matter what the integral of f is, we can take it always take it out here. And we can also take it out here and cancel. And now that we do this canceling, then what we get is, let's clean this. We get this identity here, which, let me point out, is very similar to Fatus Lemma. So we're basically applying Fatus Lemma to f without f being non-negative, just using the fact that it is not non-negative, but its negative part, it can be killed by this function g here. But now, since we have proved this for f, we could have done exactly the same thing with minus f, the same argument with minus f instead of f, and we would get the integral of minus f, the mu, is bounded from below by the limit of the integral of minus fn the mu. Now we know from properties of an integral that this minus here, it can go out. This minus here, it can go out. Well, and here it can also go out of the limit, then the limit will become a lim sup. And the minus appears out here. Well, now we have the minus on both sides. What we can do here then is, well, this minus can become a plus as long as we flip the inequality. But now, wait, we have shown that the lim sup is less than something, which is equal to something, which is less than the limit. And well, when the lim sup is less than the limit, that means they are equal, and they are equal to the limit. Because in general, the limit is less than the lim sup, and they are equal if and only if the function has a limit, in which case they both equal the limit. And since the lim sup is being bounded from above by something which is bounded from above by something else, which is the limit, then these lim sup and limit, they are actually equal limit, and this equals the integral of f. And this is exactly the statement of the theorem. So the theorem is proved. This concludes this proof. This concludes this video lecture.